of New Relic about Python profiling, so please give him a warm welcome.
So this talk is about Python profiling. So let's begin by answering a very simple question. What is Python profiling? Well, if you know anything at all about racial profiling, this is going to be nothing like that at all. So I'm sorry to disappoint the Rubyists in the crowd. We're not going to be doing this to Python. This talk is about measuring performance. I just wanted to get that out of the way. So if you want to go to a different talk, that's fine. A little bit about me. So my name is Amjith, and I'm a Python addict. I love Python. This is my favorite language. I like it better than my native tongue, which, by the way, is not English. So if I'm like totally inventing a new word, it's probably because I'm mispronouncing it. I work for a company called New Relic. How many of you here know what New Relic does? Holy shit, that's a lot. Okay. This kind of makes my next slide kind of useless, but we do application performance monitoring, which is actually just fancy talk for if you install our software on your server, we show you pretty graphs, and from that you can find out where the bottlenecks are. That's kind of what we do. The reason I'm saying this is because I may know a thing or two about measuring performance. I just want to establish that. Anyway, enough with the background. We're going to jump straight in. So you might have heard this unofficial motto of Python, which is batteries included. What that means is basically it comes with a rich standard library that if you want to do something, there's probably already a module in the standard library to do that. True to that, we have a module called cprofile, which allows you to do profiling in Python. And this is, again, it's part of the standard library, and it's actually very, very simple to use. The way you would use this is if you are typically running Python space, lcm.py, now all you have to do is python-m cprofile and then lcm.py. And immediately it profiles your script while your script is executing, and then it tells you how long it took to run, how many function calls were executed during that course of execution. And then it gives you a breakdown of all the different functions that were called, how many times they were called, how long each function took to run. And you get a wealth of information from this, from just running cprofile on your script. Now, this is a typical example where I was calculating the least common multiplier. This is a simple algorithm. I thought I did a pretty good job with the algorithm, and it turns out I was calling 7 million function calls, or I was making 7 million function calls. And about 3 million or 6 million of them was split between calling min and max. And this was called inside a while loop, and that's apparently what was causing a bottleneck there. So what I did was min and max were like invariant in my code, and so I moved it out of the loop, and then I saved it in a variable, and then I ran the cprofile module again. And now it takes about 0.8 seconds. So we dropped from 3.8 to 0.8 seconds because I knew where to start looking or where to start modifying my code. And that is like 4 times improvement. So this was the first time. This was my first code that I actually profiled. This is like a great example to show how easy it is in Python to profile something. After I did this, I was feeling like I am the master of the universe, right? This should pretty much be like the end of the talk because it's like you know all the tools you need and you're ready to go. So I figured I'm going to optimize everything that I can find. All my code, all my script, I'm going to use this and then profile the heck out of it. So I decided to run one of my longer scripts. I truncated the output here. The first time I ran this, I didn't have a scroll back long enough. So this actually dumped everything on the std out, and they were like, I only had the scroll back up to 500 lines, and I couldn't even see the top of it. So obviously I thought, there's got to be a better way. So obviously there is, which is, you save the profile to a file and then you analyze it. You load it in a tool and then you analyze it. Obviously you don't want to just pipe the std out into a file and then go through them manually. That's ridiculously tedious. Let's not do that. Anyway, to save it into a file, again, that's also a pretty simple thing to do. The cprofile, again, comes with a -o option, which lets you dump the profile in a binary format into a file. And then you can load it into a module called pstats. Again, part of the standard module. And this lets you run some kind of like primitive SQL-like queries. Like you can sort your results by a particular column name, and then you can show only the top 5 of these, 5 of the entries in that list, and so on. But I mean, this is pretty good. But we all saw what happened to the command line interface. You know, when things got a little bit bigger, it got kind of ugly. It was kind of hard to deal with. So there is a GUI version of this. It's cleverly named Run Snake Run. I hope you guys get that pun. But so this, what it does is you load this profile file that you just created into this Run Snake Run GUI, and then it produces this gorgeous square maps. Well, it produces square maps. I'm not doing justice by just showing the screenshot. Here's how it looks in real life. So when I run my cursor over a certain module, it highlights them on the left side. I can sort them by the number of calls. I can sort them by how much time it took. I can make it into a percentage or a raw time that it took to run, and so on. And it allows me to drill down. So if I double click on it, it just zooms it in, and then I can double click on this to find out what's going on, what are the different functions that are getting called inside. And this is actually quite useful. And also, again, I get impressed by bright colors. Anyway, so back here. So after I discovered that, I thought that was perfection. That's as close as you get to nirvana. There's just one catch, though. So what that is when I ran my code without the profiler, it took about 5 seconds to run. This is another different script for Fibonacci. And when you run it with the C profile, it takes approximately about 10 seconds. That's like 100% overhead. You might think it's not a big deal, because you're just running it in a dev environment, but Picard disagrees, because he wants to run it in production. If you are wondering who the hell runs their profiler in production, only the most successful company in the world. You really think that 0.34 seconds is just to like show off that they can do all this? Well, that's part of the reason too, but but I think more importantly, there is someone taking a closer look at that number, and any time it goes over a certain threshold, I am sure there's like tons of engineering money going in to get that number back down. And they are running this in production. This is an actual Google search that I did last night. So people do run it in production, and if you want to be successful, you want to know the performance as it happens. You don't want it to be running it in a dev environment or a staging environment where you send it as synthetic data. That's not going to cut it. I mean, no matter how accurately you try to reproduce your production environment, it's not going to be good enough. So what we've established so far is C profile is kind of slow. It's not production worthy. And if you're not running it in production, you're not feeding it realistic data. So what's the solution? So what can we do? Well, we don't have to run C profile on every single one of them. Meaning on your whole program, you don't need to run the C profile on all of your program. What you could do is pick critical functions and only profile those critical functions. Whenever that function gets invoked, you can turn on the profiler, capture the profile performance information from there, and then turn yourself off after that function returns. And this can be done very, very easily in Python. So here's a proof of concept, where you will notice that I'm adding a decorator called profile_func. This is not part of the standard library, but the code for that is available in the link at the bottom. I'll be putting these slides on speaker deck, so there's no need to like take notes or anything. You can continue browsing. But the point is, you can add a simple decorator on the top of the function, and it immediately starts and stops the profiler during the function execution. So we've kind of established, so this kind of proves that you don't have to be profiling everything in your program. You can just profile the critical paths. This might seem like it lessens the overhead, like the overall overhead, which is a great thing. But critical functions are the ones that you don't want to slow down. Meaning, if there's a checkout page that is critical for your business, you don't want that to like run the profiler all the time on that checkout page and cause it to slow down so that people get frustrated whenever they want to check things out. So there's still that con. It gives you a bit of a finer resolution in terms of whatever subfunctions get called from that function and how long that took and different things like that. But there's also this disadvantage that you have to go and litter your code with all these manual decorators all over the place. And sooner or later, your manager's going to tell you that, rip it all out. I mean, I don't care about profiling anymore. I need the money. So you're kind of stuck with like going and commenting it all over the code, or adding it back in is again kind of tedious. So targeted profiling kind of solves part of the problem, but it doesn't solve all of it. At New Relic, we kind of do a similar approach, but not quite as intensive as a targeted profiling. So we do use targeted profiling, and we narrow ourselves or focus ourselves down to web applications only, so it kind of narrows our vision, and we're not trying to hit every single desktop application or any of all the scripts out there. And we don't use cProfile module because that is kind of like going after a mosquito with a bazooka. So we're gonna use I'm calling it hybrid profiling. I'll go into that, how we do that in a little bit more detail. So what I mean by targeted profiling is we choose a handful of web frameworks. I'm not including all of them here, and half of them are not even showing up. But anyway, the point is we pick a few of the web frameworks, and all these web frameworks have a common pattern. Whenever you go to a URL, your request gets routed through a URL handler to a bunch of different handler functions. And all we have to do is when that gets run, we just need to put an import hook that fires a decorator that gets automatically added during runtime. So which is also in Python world we call that monkey patching. We just monkey patch a couple of functions that are critical for the user to know what the performance is. So we're not going to be capturing information about every single function that's executing, but we're doing it only for a handful of functions. And obviously, if it is a web application, I mean, there's a database involved, and then we also capture how much time is spent in the database and so on. So that's the targeting part of things. And the hybrid profiling is, like I said, we don't use cProfile, but instead what we do is we just wrap it around with timer modules. So we just take a timestamp before, take a timestamp after. We don't follow through into sub-functions that are getting called. So we capture information about the top-level function, and then we give you that. And we only capture timing data. And in addition to that, the reason I call this hybrid profiling is because we can also capture arguments. So when something slow does happen, you know exactly what inputs were passed in order to cause that thing to actually slow down. So and let me just show you an example of how it looks like. This is called a transaction trace in the New Relic UI. This almost looks like a stack trace. This is a waterfall diagram, or a waterfall graph, and you'll see from the top to the bottom where the first entry is the WSGI application, and then the next layer is the Django layer, and then goes into your view handler, and then it goes into the template modules. So it kind of follows through the execution to a very tightly, I mean, we are instrumenting all these pieces that I'm showing over here. And since we're also capturing arguments, when you want to know what's going on, so for example, I've expanded that out over there, which is, it tells you exactly what is the SQL statement that was used in creating that response for you. So that's what's the advantage in capturing the arguments. But this is not just all roses, because since we're using targeted instrumentation, there is occasionally going to be places where a bunch of time is going to be spent, which is going to say application code. I mean, no kidding, genius. I mean, it is, of course, application code, but you don't know what's going on. Well, you can go and add custom instrumentation and things like that. We provide APIs for it, but again, it kind of gets manual. So to summarize hybrid profiling, well, the pros are it's really fast because you're only doing targeted instrumentation of different functions, and it only adds about an overhead of, for our internal testing, on the worst case scenario, it'll add you maybe like 7 to 10%. But again, it depends on your function, or it depends on your application. And then since we're able to capture function arguments, we're able to provide a richer background. The cons are it's kind of semi-manual, because if you're stuck with the application code block in your transaction trace, then you'll have to add a decorator or define it in a config file or something. And it's kind of limited. That's what causes the application code to kind of show up in your stack traces or your transaction traces. So far, we've been looking at what we call as deterministic profiling, meaning when a particular execution happens, we want to time exactly how long that took. Whether we are doing it targeted manner or whether we are doing it using cprofile, those are all deterministic profiling where we know exactly how long something takes. So we're going to look at it from a different view now. I'm going to introduce a concept called statistical profiler. This is kind of not deterministic. But I want to introduce statistical profiler with an analogy. A statistical profiler is kind of like a overly attached girlfriend or a boyfriend. You're probably wondering what the hell am I talking about. So let me explain. So an overly attached behavior has three subdivisions. You get constantly interrupted. You get inquiry about what are you doing. So constant interruption is kind of like getting a phone call every hour. And then inquiry about where are you or who are you spending your time with and so on. And then you collect all that information and you do this for about a week. You can build a pretty good profile about how you spend your day and who do you spend it with on a daily basis. On Monday, how do you spend it? Tuesday, how do you spend it? And so on. Now, you may call this as overly attached behavior, and this is what I call a statistical profiler. In a programming sense, what we're doing here is we set ourselves a little bit of a timer that wakes up every 10 milliseconds or 100 milliseconds or however long, and then it asks all the running threads for its stack traces. And then it tries to build a call tree from that stack trace. So how do we set ourselves a small timer? In Python, there are two ways to do this. One is you can set yourself with sig alarm, which is a Unix signal, which you can set it for 100 milliseconds and then tell it to repeat every 100 milliseconds after that. And then it'll send you a sig alarm to your process. Or you can have a background thread that sleeps for the most of the time and then wakes up every 100 milliseconds to do some kind of an action. And that action is basically inquiry. And that's, as I mentioned, we're asking for the stack frame of every thread that is running. This might sound like, voodoo or like getting stack frame of every thread is like the really hard thing. But again, we're talking Python here. This is not like a hard language. So in Python, you can use the standard library again. sys.currentFrames will give you every single thread and the stack frame for every single one of them. It gives it to you in a dictionary where the key is the thread ID and the value is the frame object. And then you can convert the frame object by passing it into your traceback module, which gives you a tuple with file name, line number, function name, and the actual line that was getting executed, the code that was getting executed in that line. So that makes it really simple. But if you're not into writing your own statistical thread profiler, there are already existing tools out there that do this for you. So one of them is called stabproof. This is available in Python package index. This is not a standard module, but it's free and it uses Unix signals. Again, it produces the output in the command line interface. I'm not too fond of this, so I'm not going to go any further in depth, but you're welcome to take a look at this and test it out. The other one is called plop. This is a statistical profiler that was created by Dropbox, and this is also open source, available on GitHub, and they also use Unix signals, and they provide the UI in the form of a D3 call graph. How many of you here D3.js fans? Yeah. Okay. So this is kind of how it looks. So I'm going to show you the UI for that too. So the first time I used it, the 5-year-old in me was like spending the first 5 or 10 minutes like playing around with this. So it can be kind of addictive, but anyway, the size of the bubble represents how much of CPU time it's taking. So this is like how much percentage of the time it was present in those stack frames is what it's kind of telling you. So this kind of gives you an idea of where to start poking around. And let me just get back here. And obviously, being in the business of measuring performance, New Relic also has a thread profiler, and we use background threads. We don't use Unix signals because Unix signals don't work very well in Windows because it's Unix. And also, well, not that New Relic's actually supported in Windows, it's not. But if we decide to, then we're kind of stuck. But the other issue is also it doesn't work in mod WSGI because mod WSGI you're using Python inside an embedded mode, and it doesn't actually get the signals at all. But anyway, and we have our own GUI, and this is how it looks. And you can see the stack trace, and you'll notice that the arrow is pointing to like an actual view handler name with file name, the function name, and the line number that was executing at that given time. And since we are also having our own deterministic profiler that I kind of talked about, the targeted instrumenting, we can actually identify which thread was running, serving a web request versus a background task versus, if it was just running a server or something. So on the left side, you'll notice that there is boxes to choose how to filter your different threads and where the time is spent there. And so that concludes kind of our statistical profiler section. Now, we have deterministic profilers and we have statistical profilers. We're going to kind of combine them together. So this is for the grand finale, and this is kind of a project that I've been working on for the past couple months. So this is a piece that I'm kind of too excited about. There is a feature that's coming out in New Relic called Xray Sessions, which was actually in secret beta up until this point when I'm talking about it. It's not in secret anymore. It's just in beta. So if you're interested in trying it out, come talk to us and we'll hook you up. But so what this does is, let's say you pick a specific page, a checkout page again, and that's very critical for your business and you want to know as much information as possible. What you do is you run an Xray session on this, and this runs for 24 hours or 100 traces. And what we do is we collect first 100 traces that are transactions that are happening on the checkout page. And let's assume that this is not Amazon where the 100 happens in like a second, but this is a smaller shop where the 100 happens in 24 hours. Then you only get you get all those 100 transactions, and we already saw how transaction traces can be used. Now, obviously, transaction traces is only using targeted instrumentation, and so you obviously get some kind of holes in it. So in order to fill those gaps, we also run the thread profiler, but we actually scope it only for that transaction. So the thread profiler will only run on the threads that was actually serving that particular checkout page. It does not run them on the others. So any gaps that you find in the transaction trace, you can come back to the thread profiler to find out what was it and add custom instrumentation if you wanted to. So that's the statistical part of things. But we also provide you with histograms, meaning how many of my requests out of that 100 took under a second or over a second or under 2 seconds and so on. And then there's like a stack graph that gives you what are the different functions that were called while serving that page and so on. And then you get obviously the response and throughput, which is like the bread and butter of any profiling of web applications. I don't know about you guys, but this is I don't know, this tickles me in multiple ways. This is awesome. So that kind of concludes, and that's how you kind of run profiling in production. And I actually started profiling everything in my site, and this can, like I mentioned before, the overhead, we're very conscious of the overhead because the New Relic software itself is designed to run in production. This is not a development tool only or a staging tool only, although people do use it like that. So this kind of, we're very conscious about the overhead and we try to minimize it, and our internal goal is 5% overhead that's added to your web application. So that brings it to an end. Any questions or comments, anything you guys have, you're welcome to ask me.
If you have any questions, if you would come up to the microphone over there.
Sorry, it was a long walk. Can you comment about memory usage and sort of garbage collection? Because we've had issues with that. We collect large amounts of data in the
Yeah, so we also had issues with that. We had to tackle it in very creative ways. So what happened was, I don't know if you know about the people who work in New Relic, but I work with a particular person called Graham Dumpleton. He's a bit of an evil genius. If you notice his Twitter picture, you'll know why I call him an evil genius. Anyway, the point is he concocted this example where you run 100 threads concurrently. Each thread was a stack depth of 100 nodes in them. And that brings it up to like 100,000 nodes that we're having to keep it in memory and so on. And that did jump up our memory from like, I don't know, from 20 megabytes to like, I don't know, 150 or something like that, which was completely unacceptable. So what we did there was a clever trick where the stack trace actually does not change very often between two samples that you're taking, because multiple nodes between two samples are very similar, because if you are serving a particular transaction, then the functions that are involved in that transaction are kind of the same. And so what we did was we only create a function node or a stack trace node if it is unique, if it was not already created. And that way we were able to minimize a bunch of the memory usage that we were accruing over time. That was one technique. And then the other technique is, I don't know if you know about Python's intern strings, which is basically if there is a string that is present in, that was already declared in the Python's VM, and then you try to assign the exact same string, like you just type it out in a different variable. Typically, if it is over 20 characters, it will try to it'll try to create another memory string. But if you intern them, it'll look up in its internal dictionary to see if that exact string was already created or not. So that saves you on memory with a additional, very minimal overhead in terms of CPU. So those are some techniques that we used. Yeah.
Anyone else?
For C profile, have you looked at any of the other graphing tools around? Like, I don't know, I've done dot graphs and stuff like that from C profile output. Have you looked at that at all?
I'm sorry, what is a dot? You
okay.
Dot
So basically, from C profile, you can output files that can be interpreted by the Unix dot command.
The GraphViz and so on?
Yeah, GraphViz and stuff like that.
I did not. I didn't know that you could actually output from C profile that could be read directly into a dot thing, but that's an interesting idea.
Yeah, so that's another way to look at the stuff. And you can get graphs similar to what the D3 producers.
Oh, nice. That's awesome, yeah. Thank you.
Did you think about adding statistical profiling into Python itself?
I'm sorry, what was the last piece?
You told about statistical profiling,
yes.
Right? Did you think about adding this one into CPython core?
The question was, has there been any consideration into trying to add a statistical profiler into the Python core?
Exactly.
Oh, to add it to the Python core? So it already gives you what you want, because the standard module, like I showed you, if you do sys.currentThreads, it actually gives you all the stack traces of all the currently running threads. So we are in fact using the standard module. We're just building a tree out of all those stack traces. So we can't expect, that's a good question. So we could replace C profile with a stabproof or something like that, is what your question is. Currently, there isn't one, but that would be something to consider. But Python standard module already gives you all the tools that you need in order to build your own. And it's not that hard, actually. It's less than 100 lines of code to create your own statistical profiler. I think the visualization part is the hard piece. And cprofile already doesn't do a visualization. I mean, the run snake run that I talked to you about, that was also a third-party one that you have to download from Python package index. So I think adding it to the standard Python module as a stat-prof or something like that, that's a good idea, but you still need to visualize it in a sensible way. So that piece, I'm not exactly sure how you would include it to Python core.
Thank you.
Sure.
Hi.
Hi.
I was just wondering if you had any tips for memory profiling specifically, because it seems like a lot of tools for CPU.
Yeah, that's a bit of sticky subject. So there was one called HEAPY, which was a research project, and I had to read through the thesis a couple of times in order to understand which commands I can use, and I kind of gave up after the second time because I couldn't fully understand. But there is a simpler one called mem_profiler, which gives you line by line. So if you run Python-m, or it's not even -m, you can look up mem_profiler, and what it does is it runs your program and then it tells you on every line how much memory was allocated on every line. But the problem is it's actually slower than cprofile. You can run it in development, but it's not very good to run it in production at all. You can get a gross idea of how much memory is being used by looking at the Unix proc file system, but that's just a gross estimate. It doesn't give you like function level granularity or anything like that.
Okay,
Yeah.
thanks.
We are actually out of time. If you have any more questions, please feel free to come up here for a bit, or we can set up an open space if necessary. Thank you all for coming. Please give them a round of applause.
Thank you.